right-hand side, but let me see if I can fix this. There you go. Now it should work. So it's right and left.
Oh. So I just real quick before like jumping into it, general motivation for this is there's a lot of exciting new applications with like augmented reality, smart cities, um, vehicle communication, and sort of a backhaul infrastructure would be wireless. You could have roadside units, you could have fixed wireless access, you could have normal deployments, etc. So one of the big challenges is to be able to enable high data rate applications, you need access to a lot of bandwidth to be able to have high data rate. So a big problem is the spectrum is very congested at sub 6 gigahertz. So we've been looking at millimeter wave or higher frequencies as a way to have access to higher amounts of continuous bandwidth to be able to enable these high data rate applications. One of the problems with using millimeter wave as a technology enabler is it has high associated path loss. As you increase your frequency, there are properties with the antennas that causes that. So what this leads to is essentially our research, which is in measurements and modeling of millimeter wave propagation in dense urban environments, specifically in Manhattan, New York City. So we've split this up into many different scenarios that have spanned from 2019 all the way to present. This is split up into outdoor to outdoor, which is kind of your more traditional case, outdoor to indoor, around corner / over top. And then we're ongoing is backscatter sensing at both 28 and future would be at 140. So first of all, the measurement equipment that we use is built by Bell Labs, and it's a narrowband channel sounder that operates at 28 gigahertz. It's got two components, an omnidirectional transmitter and a rotating 10-degree horn antenna receiver. The horn antenna essentially collects a power measurement every degree and saves those onto a Raspberry Pi for later processing. So all those values are in dBm, so it's a properly calibrated system. Unlike some of the yellow box PAMs you see there, there are some unknown gains with those. So the first measurement setup is, as I mentioned, kind of like the traditional setup. So this is where the receiver is acting as the base station and the transmitter is acting as the UE. So essentially the transmitter and receiver are stationary for the duration of the measurement, which is, let's say, about a minute. And then the transmitter is basically, it travels 1 meter, 1 meter, 1 meter across the sidewalk, right? And essentially, we try to model the path loss in different cases, right? In the outdoor to indoor scenario, so actually outdoor to outdoor happened before I started the PhD program, and then I joined and then I started helping with outdoor to indoor. And the application for this was really interesting to me. So actually, you may not know, but New York City, 40% lack internet connectivity, like comprehensive internet connectivity. That means home and mobile. That was in a 2018 Internet Master Plan report by the New York City CTO office. And in fact, actually in the Cosmos deployment area, 29% lack internet. And the logic behind it is, while New York City, in Manhattan, there's lower part that has a lot of economic return for these network deployers. In upper Manhattan, there may not be as many businesses, so it becomes not as much of a benefit to them to deploy these networks. or it's cost prohibitive towards people who want to buy them or to have the service. So in this master plan, one solution people were looking at were, can you use millimeter wave fixed wireless access as a potential fiber alternative to be able to sort of, beam signals into like public schools, classrooms, NYCHA housing, and provide internet connectivity to those who may not have it. So what we did was we used this Bell Labs like the base station or the fixed wireless access. And then the receiver is indoors. So that's actually next to a window. You're not seeing the window, but it's about 1 meter away from the window. That's sort of representing like an indoor customer premise equipment or indoor CPE. But you'll also see other cases where they have them outdoors as well, but there's a wire that goes in, but it's up to you. Then the other one was, so if you followed the news, you'd see that millimeter wave had a lot of issues, especially with blockages in urban areas, especially when you lose that line of sight, then the signal drops a lot. So we looked at the around corner case. So this is where the base station is like in one of these 9 locations. But basically, the transmitter kind of turns the corner, so you can see in the visual there. And we kind of, essentially want to see how far into the corner can you go before you lose your signal. But in these two, these are a little different because actually the base station, the receiver, is above the local clutter. So clutter meaning like the top of the nearest like building, right? And in that case, we wanted to see, does the signal propagate over the top of the buildings? If it does, is it useful for multi-user MIMO? So in the green here, this is the FCC innovation zone. So the vast majority of our measurements were taken within the FCC innovation zone. There are a couple that were just outside of it. For those, we had an experimental license. But each dot basically represents a different location of the receiver. And then the line represents the path that the transmitter took for the measurements, right? So this is the outdoor to outdoor scenario. This is outdoor to indoor scenario. So you can look at the numbers here. There's a lot of measurements we took, right? We're talking about millions of individual power measurements. So if you think about it, this channel sounder, it's rotating, collecting 1 power measurement every degree. Usually it collects around 40 turns of the sounder for 1 actual point in our final plots. And we collect, hundreds of these, and they accumulate up, right? So you've got millions of individual power measurements, thousands of actual individual links, a diverse set of scenarios and buildings and material types, et cetera, right? So a lot of more, at least in the context of this, more data gives us a better model. And then for the, there's a slight typo here that is not supposed to say 979 million. That is this 979. My bad, but you get the idea. In this case, it was a little different because we collected measurements in. Hello? Oh. We collected measurements in Upper Manhattan, and then Bell Labs collected measurements in Lower Manhattan. Hello? Okay. Yeah, so we combined them to create an even more generalizable model. Um, yeah. So first I'll talk about the outdoor to outdoor and outdoor to indoor scenarios. So let's first look at outdoor to outdoor, right? So the first case is what happens if you change the height of your transmitter. Moral of the story is not a huge difference. However, if you have foliage versus no foliage, that has a big, like a 10 dB difference, right? So that's not insignificant. If you swap the transmitter and receiver, there is not a tremendous amount of difference. Now, in outdoor to indoor, this is really interesting. There's different types of glass, right? So there's like older glass will not have the UV protection coating. Newer glass will, and that coating actually creates a noticeable like 20 dB drop in power. So the penetration loss is really interesting. Actually, it's interesting for the application if bridging the digital divide, where I'll talk about it in a second, but in like the public school or NYCHA housing, they probably don't have low E glass, right? So actually that's a good thing. So we found you can get up to like, if you do like a general estimate, like a gigabit per second data rate, it's not bad. And then we looked at what happens if you have a subway track. I mean, these are like very practical things that you would see in an urban environment. And I think the point is like, we're able to use the FCC Innovation Zone to be able to actually see what the effect of these very real things are, right? Some of these things you can't always put in ray tracing, right? So it's nice to actually see what the data looks like. And then also like comparing what happens when you change the floor that your thing is. And then around corner is not surprising, right? It's not great. So but it's actually, it's more about, I think, like modeling this. So if you look at 3GPP's like urban microcell non-line of sight model, if we apply that to our data, we would get about 11.9 dB RMSE. But if we use our own, if we use our model that's adapted from Bell Labs, then that'll give us about 6.4 dB RMSE, and we further evaluate this with like k-fold cross validation, and because we have so much data, we can start like training on some parts of it, testing on another part, and like kind of validating how accurate this model really is. And then for that, we can get some estimates of how much data rate you'd expect, namely like how much it would drop after you go like 10 meters into a corner or something like that. For the other measurements is for the over top case. This was really interesting. The sort of, as the transmitter is moving, so the transmitter is like the red, right? So if it's moving behind the buildings and then the receiver's placed here, if you look at the angle of arrival of that signal, that's kind of what's plotted here. So blue is what happens before the corner. So that's like the line of sight link, right? And then orange is what happens after you turn the corner. So, and then the x-axis is distance, the y-axis is angle, peak angle. So you can see very, and the black line is kind of the geometric ground truth. So like if you literally just drew a straight line, where would that point, right? So it deviates by only 2 to 3 degrees of the ground truth, which is great for multi-user MIMO because if you think of antenna arrays like that, which have 4 different independently controllable ICs, you can beam steer to 4 users and track them and do all kinds of things, right? So some of the work that's ongoing now is kind of more in sensing. So on a simple scale, what happens if you plop the transmitter over the receiver, right? So the transmitter will send omnidirectional signals everywhere, right? And those signals will scatter from all the objects in the environment, especially things that are made of metal, that'll reflect a lot. And one problem is if you want to place a transmitter on top of the receiver, how do you isolate the self-interference? So we use, advanced wireless, we use aluminum foil to block it. But it works well enough. We've run open field measurements to actually measure what that is and quantify the noise floor, or the sensing noise floor. And yeah, so we're like an ongoing effort right now is to collect these sensing measurements in different intersections. So here's like kind of some preliminary like data that we have where we've gone to many different corners, and you can see some reflections here that generally correspond to light poles or really strong reflectors like food trucks, for example. But there's also something really interesting about this background, right? Because if you think about like a joint communications and sensing platform, this might be like your channel, right? So like trying to understand how to model that, how to generalize it, how to create a way of figuring out what that looks like for any urban environment so a network deployer knows what to expect. Oh, and this is kind of like it's like a nice little example of, so here's an intersection. You saw the same intersection in Jorge's presentation. The left plot is when this bus was not there. The right plot is when the bus was there. When the bus was there, the power increased by about 32.7 dB. So that's you can think about how to use that to your advantage with different objects, right? Well, some of the future work that we're looking at is now using a 140 gigahertz channel sounder. It's the same principle, but one unique feature is that the antenna is a very small beam width and collects many samples per angle. So it's not just one sample per angle, but now like I think like 5 or 6. So we're trying to look at how to take the same scenario, but also now see if we can integrate it with what you hear is multimodal sensor fusion. See what can be done there. That's I think that's it. Yeah. If you have any questions, let me know.
Time for a quick question? Yeah, okay.
Can you estimate in a given area how many base stations you need to deploy that? Because I suppose that the purpose of this fixed wireless access is that to eliminate the many base stations you need for deploying things at 28 gigahertz, right? Yeah. So you use, let's say, the C equipment as a transmitter to go to around the corner, etc. Yeah. Have you made this estimation because it's economy aspect? Yeah. If you need many base stations to do that, it's not worth it. I mean, you have to eliminate base stations, right? That's the purpose of all these kind of things.
Yeah, I mean, like so first is yes. We looked at different like pre-corner distances. That was like one of the plots that I showed. So we looked at like if you'd have 100 meter pre-corner distance, meaning you have a separation from base station to base station of 100 meters or 200 meters. How did that changes? And you can model this, right? So part of the thing is with our model, with 6.4 dB RMSE, you can incorporate exactly what you just said. But the reality is there's also many different geometries to each street and other factors to consider, and not to mention the whole, how do you create an like a business argument for that? That's a different, that we're, right now we're just modeling the propagation, and it's up to you to use that model to understand how that fits your deployment strategy. But yeah, or not, which is what we, yeah.
Come on, you can never have too many base stations. Come
Yeah.
on.
Exactly.